This is the first lecture of a series of 4 lectures concerning the classical description of the electron, of the spinning electron. The electron is an elementary particle, and therefore, as it is considered one of the ultimate objects in the division of matter. It is therefore a very simple material object. The usual classical description of the electron, taking this idea of simplicity, is just by assuming that the electron is described by the simplest geometrical object, the point. So we used to deal with electrons by considering them points where we attach to them the mass and the charge of the electron. But this description is not completely realistic because the electrons have a spin. Spin is a mechanical property associated to bodies which rotate. The Earth rotates, and associated to rotation there is a mechanical property called angular momentum. It defines the rotation axis, and therefore the Earth has angular momentum. A top, if it does not rotate, it has no angular momentum, but the top, if it rotates, it has angular momentum. You see the difference between a top at rest without rotation or top rotating, they have a different dynamical behavior. Okay, the same thing happens to the electron. If we consider that the electron has no angular momentum, and if the electron has angular momentum, the dynamical behavior will be different. We used to reserve the name spin for the angular momentum of elementary particles. So the goal of this series of talks is to give an answer to this famous sentence by Albert Einstein: if I cannot picture, I cannot understand what I'm talking about. About picture, what I mean is this idea of describing how the different parts of the electron are moving, if it has a shape, how it rotates. And because it is an elementary particle, the idea to describe an elementary particle will be at least to try to understand the electron. The remaining lectures are these. The first one is this one. The second lecture is devoted to the analysis of the tunnel effect. Quantum mechanics books say that tunneling, the tunnel effect, is a pure quantum mechanical effect without classical interpretation. Well, this is not completely true, because the usual classical interpretation is performed with the spinless point particle model, and therefore it is a simplified model of a spinning electron. It describes an electron without a spin. What we shall see is that the tunnel effect, the spin plays a fundamental role, even the spin orientation. The third talk will be devoted to something which, from the classical point of view, it is unusual. 2 electrons, because they have the same charge, repel each other. So it is impossible to form classically a bound state of 2 electrons. I can form a bound state between an electron and a proton, a positive and a negative charge. Hydrogen atom is one of these examples. But if the 2 particles have the same charge, it is impossible, from the classical point of view, to form a bound state. Nevertheless, electrons are not point particles, they are spinning particles. And if we have 2 electrons with their spins parallel, we can show that they can form a bound state of spin 1, which is stable up to quite a high temperature. And therefore, if the conducting electrons of a conductor, all electrons are paired, forming a system with spin 1, they are bosons. And the conduction with bosons in a conductor implies that the conductor has reached a superconducting phase. The last and 4th lecture of this set of lectures will be devoted to the introduction of the dynamical equations of the spinning electrons. They are differential equations for the model we are going to introduce in a few moments. Now, the formalism we have developed gives you this classical model of a spinning electron at rest. Electron at rest means that the center of mass of the electron is at rest. We don't know what is the shape or size of the electron, but the only feature is that it has a center of mass, here M, and a center of charge E. And the center of charge, it is moving around the center of mass at the speed c. Now, this suggests that this object, for the center of mass observer, is rotating and therefore it has a spin. And the spin has two parts because this object has 6 degrees of freedom. The 6 degrees of freedom we need to describe are the coordinates of this center of charge, the 3 coordinates, and also 3 parameters which describe, associated to this center of charge, a co-moving Cartesian frame which rotates with angular velocity omega. So associated to these 3 degrees of freedom which describes this orbit, there is a part of the angular momentum which I call z, and associated to the other 3 degrees of freedom, there is a part of the total angular momentum along the angular velocity, so that the total spin is the addition of these 2 contributions. The mechanical features of this object are these. When quantizing the system, the spin is unique. It's spin 1/2. The electron has no excited states. So the only angular momentum of this object is 1/2. The radius is half quantum wavelength, 10 to the minus 13 meters. The frequency, the number of turns per second, is 2.5 plus times 10 to the 20 turns per second. Or alternatively, the period is 4.10 to the minus 21 seconds. But because it is a point charge describing a loop, the current associated to this charge times the area of this loop produces a magnetic moment which is related only to the orbital part of the angular momentum z, but when quantizing the system, this part z is twice as much as the total spin, in such a way that when we represent the total angular momentum in terms of the total spin, we get this 2 here, what is called a zero magnetic ratio. This model quantizes, and when it quantizes, satisfies Dirac's equation. So it is not strange that when we compare this data, which Dirac in 1928 obtains from the relativistic model for describing the electron, he obtains that the electron has a spin 1/2, that the velocity of the electron is c, that oscillates in an area around 2 times this radius, this is Compton's wavelength, with that frequency, with that period, and it has a magnetic moment with g equals 2. Okay. One of the fundamental principles of our formalism is the restricted relativity principle, which states this sentence, that there exists a class of equivalent observers who write the laws of physics in the same form. Okay, for all these kind of equivalent observers, one of the laws that is satisfied is the law of inertia. The law of inertia means that for an arbitrary inertial observer, everybody, or it is at rest, or it is moving at a constant velocity. So the equivalent observers are called inertial observers. An accelerated observer is outside this set of equivalent observers, because if I see free motion of a particle of a straight line of the center of mass, the accelerated observer does not see a free motion, so it is discarded. So we are going to make physics only for this restricted class of inertial observers. Okay. This set of inertial observers are either at rest with respect to each other, perhaps with different orientations, but if they have a relative velocity, this is a constant relative velocity. But this constant relative velocity is unrestricted at first in this part of the analysis. Now, one of the other sentences attributed to Albert Einstein is this: everything should be as simple as possible, but not simpler. So if we have a model of a spinning electron and suppress the spin of the electron, we get simpler models like the point particle system. For instance, the point particle represents an elementary particle without spin. So thorough simplification will lead to unsuccessful description of physical phenomena because we are suppressing an important mechanical property of the electron. Okay. But in nature, it seems that there are no spinless elementary particles. 20th century physics has shown that all known elementary particles of nature, electrons, muons, quarks, photons, all of them have a spin. So if all elementary matter, all elementary particles have a spin, it is unnecessary to make that description of elementary particles in terms of point particles, so that we have to abandon the excessive use of point particle model to analyze physical phenomena which involves always spinning particles, and the spin is going to play a relevant role. Now, the spinning particle model we introduced in the first picture is a mechanical system with two different centers, a center of mass and a center of charge. Let us see the following discussion concerning these two features. Now, for an inertial observer, an elementary particle is a mechanical system that has mass, and therefore it will have a center of mass. Okay, but elementary matter interact. If they interact, they will have some kind of charge, for instance, electric charge. We describe the interaction between charges in terms of points where charges are located, and the interaction is expressed in terms of the separation of the charges and in terms of the velocity of the charges. So, if the electron has charge, it will have a center of charge. So, in general, we have two different centers, one associated to a mechanical property, the mass, and another associated to an interacting property, the charge. Only two things can happen: that both points are the same or that they are different. Unfortunately, particle physics has selected the first option, the simplest one, the point particle. But the point particle model describes an existent spinless particles. They do not exist. And therefore, particle physics has to try to understand what happens if we have an object with two centers. We have to analyze this second possibility. Now, to analyze the second possibility, let us see how a particular inertial observer describes the free motion of a spinning particle with two centers. Well, if the particle is free, we will see a straight motion for the center of mass, because if there are no forces, the center of mass of the system is not accelerated, and therefore it moves at a constant velocity. If the center of mass is at rest, and the particle is rotating, what we will see is that the center of charge will be rotating at a constant velocity. But if the center of mass is moving, we will see a center of mass moving at a straight line and some kind of helical motion for the center of charge at a constant velocity of constant absolute value. Why of constant absolute value? Well, because if the absolute value of the velocity of the center of charge is not constant, it means that in this point the velocity is different than in any other point. And if the velocities are different, this will mean that some kind of external torque or something strange is happening at these two times. These two times cannot be distinguished. We cannot distinguish in the evolution of the center of charge one instant of time from any other if the particle is free. Okay, this is the description I make as considered as an inertial observer, but this description must be valid for any other inertial observer. Oh, and this presents a very strong constraint. The first conclusion is that the center of charge can never be at rest for any inertial observer. Why? Well, let us assume that we have the center of charge moving along this helical motion, and in this instance we have some inertial observer located very close to this point and moving with the velocity of this point. So it sees the center of charge moving at zero velocity. But because this has an accelerated motion, at the next instant it will be moving with a non-zero velocity with respect to this inertial observer. So for that inertial observer, the motion is not at a constant velocity, contrary to the idea that the motion must be free. Well, this means that there exists a limit velocity for the center of charge, which we call c, unreachable for any inertial observer. But according to the relativity principle, if this limit velocity exists, it must be the same for all inertial observers. Okay, because if we have this motion, the velocity of the center of mass is below the velocity of the center of charge, so the center of masses of the bodies can never reach the velocity of the center of charge. So the existence of an elementary particle with two different centers require that in nature must exist a limit velocity for the motions of the bodies. Okay, this kind of analysis implies that the formalism which describes elementary particles and their possible interaction has to be done in a relativistic context. Okay, in this sense, and with this idea, recently we have published this paper in which we obtain the relativistic formalism for inertial observers, that is the Lorentz transformations, without any reference to light or to other electromagnetic phenomena, just by assuming that there exists a velocity limit between inertial observers. So, inertial observers necessarily are related by the transformations of the Poincaré group. If there is no this velocity limit, this transformation must be obtained just by the transformations of the Galilei group. Okay, let us see how is the free motion for a free electron with two centers. This screen represents the numerical solution of the differential equations of the model, differential equations which I will introduce in the last lecture. So in this screen we are going to describe the motion of both points. I sent the electron along zeta axis with a velocity which is 0.3 of the speed c. The spin is oriented 30 degrees, and see what happens. Okay, this is a typical motion for an arbitrary inertial observer, a free motion. This is the typical motion where the two centers are this, but the nice feature is that the center of mass velocity is always below c, and the center of charge velocity is c. What we see here is that the electron has an internal periodic motion, and therefore the electron is a clock. But a nice feature is that when the center of mass moves, you see it takes more time to give a turn. For instance, these 2 points represent the initial position of the center of charge and the position after return. The length of this path is larger than the length of the path when the center of mass is at rest, because in both cases this path is followed by at the same velocity c. This takes more time to do this path. In fact, the time in this case, capital T, is gamma of v. Gamma of v is the relativity factor times the time for the center of mass observer. If I see moving the electron, its local clock is moving slower. Then, if I see some inertial observer moving with respect to myself with a certain velocity, all its electrons, all its local clocks are moving slower than my own clocks. What I see is a kind of a slow motion of all electrons associated to any other inertial observer. So that any time measurement, if it is performed with these local clocks, is of course relative to every inertial observer. So time is relative. Now the formalism is described in this book, or alternatively you can get these documents which corresponds to to a lecture course I lecture at the University of Basque Country. You can contact me. All calculations of this formalism has been done by hand with Mathematica, and the numerical integrations with Mathematica with this program, Dynamic Solver. And the next videos, as I mentioned in the introduction, will be these 3. Okay, thank you very much for your attention.